here we have a cylinder of mass m and radius r. It is on a surface which has got some friction so that there is no slippage between this and this. This can roll over this surface, and from the center a pendulum kind of a rod is vertically hanging, and friction over here is equal to 0. The length of this rod is L and mass is same as that of this cylinder. We know that is moment of inertia of cylinder about this axis is mr square by 2, and the rod is obviously about this center of mass is going to be ml square by 12. We have done it when we had done moment of inertia. Now force F is applied in this direction, F is applied, then this is free to rotate like this about this. But when the force is applied, then certainly this will also move in this direction and this will also move. We are asked what is the acceleration of this point B as well as A, that is on the axial. So what we do is, as usual what we have been doing is, we draw the free body diagram of this cylinder separately and of this rod separately, and then we shall be dealing with the linear equations, that is F is equal to ma, that is we are talking about linear mechanics, net force is equal to mass into acceleration, and then we shall also be making the equations, that is torque is equal to I alpha, and then we see that is somehow can we connect these two equations, that is the net acceleration is going to superimposition of vectorially of the accelerations, and from there we will see that is how we can proceed further. So let's start making the equations. For this, when the force F is applied, that is onto this, if the force F is applied, then because this force is applied through this rod onto this center, onto two axial, there is some force applied that is equal to F dash. When this rod applies a force F dash onto this, then this will apply back. So this will experience a reaction force. So to have reaction, there is equal and opposite reaction. So when this rod at this axial applies a force F dash onto this, this will also experience a force in the backward direction. To have reaction, there is equal and opposite reaction. So when it tries to rotate over here, then obviously the friction force will be acting in this direction because there are irregularities. This will try to slip over there, irregularities they are there. As a result, this will experience a friction force in this direction, and this is going to have alpha in this direction and acceleration also in this direction. We have said this acceleration is A2, and suppose alpha, angular acceleration is alpha. So A2 is equal to R alpha. Also, F dash minus F net force is equal to mass into acceleration. We have simply used Newton's laws of motion, and over here that is A is equal to R alpha, that is A tangential is equal to R alpha. We have used that. Coming to this. So when we come to this, so net force F is over here, F dash is over here. Obviously the center of mass will be moving in this direction. When you apply force, center of mass will move, accelerate in this direction. So F minus F dash is equal to M into A. We have said that is A1, acceleration of this is A1. Also, if we take the torque about C, torque is equal to Y alpha. Now we have to see that is this force which is applying in this direction, which is being applied in this direction, and this being applied in this direction. Both of them, they are contributing towards the clockwise movements. Both of them, they are trying to move it in the clockwise direction. So F1 into L by 2 plus F into L by 2, that is a net torque. Now we intend to use net torque is equal to Y alpha. So net torque F1 plus F dash L by 2 is equal to I about this is ml square by 12 into alpha. So now we have one is this equation, the second is this equation. Now we also know that is this point A is common for this also and this rod also. So this is going to have a one single acceleration only. So whatsoever the acceleration of A2, the same will be acceleration of this point A also. So acceleration of this point A, and this is a common point. Over here we have said A2 is equal to R alpha 2. Okay, that's fine because from here we have got A2 is equal to R alpha 2. But what about from here? From this we get two accelerations. One is A1 because of this linear acceleration. The second is because of A is equal to R alpha. So this point is also going to have acceleration of, that is A1. A1 will be in this direction. R alpha, A tangential is equal to R alpha, that is A tangential will be in this direction, and its value will be A tangential into R alpha. That is the A tangential will be in this direction, and that is equal to L by 2 into alpha, where alpha is of this rod. So one is we get A2 is equal to R alpha 2. This is one we get. And from here if we see, the acceleration of this point is number 1, A1 is in this direction, and R alpha, that is A tangential is equal to R alpha in this direction. So we get A1 minus L by 2 alpha. A1 gets superimposed over here vectorially, and R alpha, because of this alpha, it is going to have A tangential in this direction is equal to L by 2 into alpha. This is the thing. But this point is common for this and this. So this one point cannot have two accretion. This is going to have one accretion only. So whether we say A2 or we say A1 minus L by 2 alpha, they should have the same value. So from here we get accretion of A is equal to A2. Obviously accretion of A is equal to A2 is also equal to A1 minus L by 2 alpha. So from here we get the value of A2 as 2F by 11m. So we get the value of accretion of point A. We get the accretion. And what will the accretion of this? The accretion of this will be A1 plus L by 2 alpha, because alpha is in this direction. So A tangential will be in this direction, L by 2 alpha, and A1 is already in this direction. So A1 is already in this direction. So net accretion of this is A1 plus L by 2 alpha. When we put the value, we get 14F by 11m.